So, till now we were in the quest for material in which delta n could be equal to 0. So, we were looking out for that, and I gave you a hint in the previous lecture that such a material could be a birefringent material. Okay. So, let us see what an anisotropic and birefringent materials are anisotropic crystals. So, we have to find a material where n omega and n 2 omega are equal, then only delta n will be equal to 0. Such a thing is possible in anisotropic crystals. Okay. So, what do I mean by anisotropic crystal? Total anisotropy is a result of anisotropy in the properties of the individual atoms and also in the anisotropy of their ordering in space. Anisotropy in a medium is defined with the help of the permittivity tensor epsilon. We have come across this entity before, epsilon, and the moment I say tensor, it means epsilon is, the value of epsilon is different in different directions. Okay. We had also come across the dielectric D is equal to epsilon E. So, the dielectric is dielectric tensor, we had called it. So, let us stick to the permittivity tensor and see what can be done. Okay. And we will define this permittivity tensor for different kinds of crystals, mainly anisotropic crystals. So, I will just give you a general idea of crystals itself. Okay. So, you can get anisotropic crystal, you can have isotropic material, and you can have birefringent material too. Okay. So, what you see here, this cubic kind of a structure, that is the real thing, real crystal. Okay. And what you see inside an ellipsoid, which is the imaginary part, but I will just explain what. It does a lot of explaining. Okay. Many results concerning the phase velocity or the ray velocity or the direction of vibration can be illustrated by geometrical constructions like this ellipsoid, okay, or a sphere, all in Cartesian coordinates, okay, for the moment in Cartesian coordinates. So, my crystal, this what you see here is the real thing, and this ellipsoid here is an imaginary part. Okay. What does it describe? This ellipsoid describes it is basically the tip of this permittivity tensor, all around in different directions of the crystal. So, this permittivity tensor has a major axis as Ex, and two minor axes are epsilon y and epsilon z. Okay. And if you were to write an equation for an ellipsoid, it would be x square upon Ex square plus y square upon, no, not E, call it epsilon y square, plus z square upon epsilon z is equal to 1. This is the equation of an ellipsoid, of this ellipsoid. So, this ellipsoid is a kind of an imaginary character which describes the value of permittivity tensor epsilon in the different directions of the crystal. So, how can I represent the different values of the permittivity which are differing in the different directions of the crystal? One way of doing it is by this construction of an ellipsoid. Okay. You can very well derive it, it is a very long derivation, you can derive it. I am not going to get into the derivation here. Those who are interested can study from the book by Born and Wolf, and he derives this. Okay. For the moment, take it, trust me, that this ellipsoid describes the different directions, okay, of the permittivity. And because this permittivity is equal to root of the permittivity is equal to n, the refractive index, and the refractive index is equal to c by v, the velocity of the ray. So, the velocity and the refractive index are also sometimes described by an ellipsoid. It is called a sphere of velocities or ellipsoid of velocities, or it can be called the index ellipsoid. Index means refractive index. So, as these primary axes, major and minor axis, you could put them as the refractive index, or you could put them as the velocities, and all of them will more or less describe an ellipsoid. Okay. So, a crystal in which all these directions have different permittivities, have different refractive indexes. So, obviously different velocities in these different directions are called anisotropic crystals. Okay. Suppose epsilon x, epsilon y and epsilon z are equal to say epsilon m, they are equal. They can be described by a sphere, x square plus y square plus z square is equal to E m square. You match this E m's, these directions with one of the Cartesian coordinates, and then you describe a sphere. Again, so this sphere is just a special case of an ellipsoid, but then if you have a sphere for that particular crystal, that means the permittivity is the same in all direction. That means epsilon becomes a scalar quantity. It is not a tensor any longer, because in all direction the epsilon is the same, and so the refractive index is also the same. Okay. Such a medium is called an isotropic crystal. It may as well be an amorphous medium, which is also an isotropic medium. So, I have this distinct anisotropic medium, and the special case is an isotropic case where all the axes are equal. Okay. Now what will happen? If I have a crystal which has this property that some rays see a refractive index which is equal in all directions, and some rays in the same crystal sees a refractive index which is different in different directions. I have just tried to make an animation that the sphere is embedded in the ellipse. It's just an imaginary thing. So, for certain rays the sphere comes into play, the sphere of indexes, refractive indices or permittivity, and in for some rays the ellipse comes into play. Okay. So, this is a birefringent crystal. A birefringent medium specifically refers to an anisotropic medium where the refractive index difference causes light to split into two distinct rays, the ordinary ray with constant refractive index and the extraordinary ray with variable refractive index. Okay. So, that is exactly what I showed you with the quartz crystal, where you see a spot. You do not see one spot when you see through the quartz crystal, you see two spots. So, in that quartz crystal you have this imaginary sphere and ellipse. So, for the ordinary ray it splits up into two, you see two spots there, it splits up into two. One of them follows this rule, and while the other ray, extraordinary ray, follows this other rule of the ellipsoid. So, the extraordinary ray is following a different set of rules and the ordinary ray is following a different set of rules. Okay. And the ordinary ray follows the Snell's law, the extraordinary ray does not follow the Snell's law. So, travelling in a crystal like this will give different refraction for the rays, different reflection for such rays. Okay. Now, a birefringent crystal, by the way, is an anisotropic crystal, but any anisotropic crystal need not be a birefringent crystal. So, since our aim is to get delta n is equal to 0, we will concentrate on the birefringent crystal where delta n is equal to 0 is possible. Okay. So, we will study a little bit, learn a little bit more about this birefringent crystal. Okay. So, before that let me just classify crystals into group 1, group 2 and group 3. 3 equivalent directions are there and mutually perpendicular directions are chosen, and Ex equal to Ey is equal to Ez equal to Em as I have shown before, the crystal is isotropic. In group 2 there is an axis of symmetry, okay, one particular axis of symmetry or one particular direction in that crystal, which is quite often called the optic axis, and it has Ex equal to Ey, but not equal to Ez. Okay. So, two of them are equal, Ex and Ey, sorry I am all the time saying Ex and Ey, it is epsilon x, epsilon y. Epsilon x and epsilon y are not equal to epsilon z. Such a crystal is called optically uniaxial. Okay. Crystal in which no two equivalent directions can be chosen. Here epsilon x is not equal to epsilon y and not equal to epsilon z. These crystals are optically biaxial. Okay. Another way of looking at it is through this ellipsoid, through this construction of ellipsoid. Another way of looking at this classification of crystal. Okay. So, I have an ellipsoid here, this is an ellipsoid, and this special direction which is called the optic axis, I match one of the axis of the refractive index. Here from epsilon x I have converted to nx and ny, epsilon y I have converted to ny, the axis I have put it that, because finally we are interested in the refractive index. They are not very much different. So, I have written the ellipsoid equation as x square upon n square x, n square y, n square x is equal to 1. Okay. So, these are the axes. So, I have this ellipsoid and one direction is the optic axis, that special direction, it has a special symmetry. And suppose I cut this ellipsoid in the center, okay, and absolutely perpendicular to the optic axis, then I will get a circular structure. The yellow part is the circular structure. Okay, and I have shown nx and ny here. They are actually, if it is circular, nx equal to ny, okay, which corresponds to the group 2 of crystals. So, if two principal axes in the ellipsoid are equal, it becomes an ellipsoid of revolution about the third axis. There is only one optic axis in this case. This third axis is the optic axis. It is a special reference point. You could call the optic axis as one imaginary line which is perpendicular to this circle, okay, but then it has certain specific properties and it becomes like a reference point for all other directions and all other and the electromagnetic beam or the ray, okay, that becomes like a reference point, but it has certain specific properties too. like for example along the optic axis, the E ray and the O ray sees the same refractive index. Okay. But the E ray, if you have a direction somewhere here, the E ray sees a different refractive index. Though the O ray in any case, wherever it goes, it sees the same refractive index. We have to bother about the E ray only, which has the same refractive index as the O ray along this axis, but not in any other direction. Suppose the direction is here, from here, if you take from the center, the E ray will see a different refractive index. Okay. Now, there are crystals where you have two optic axes here. So, this crystal falls actually under this group 3 crystal. It is proof that an ellipsoid with 3 different values of the principal axis have 2 circular cross sections. This medium has 2 optic axes. Crystal with 2 optical axes are called biaxial crystals. So, under this third category, where nx is not equal to ny is not equal to nz, you have this kind of a circular piece. You can find 2 circles within that same ellipsoid, okay, and those perpendicular to it is the optic axis. All right. Okay. So, let us go to the next slide. Now, you have understood these are there is a biaxial crystal and there is a uniaxial crystal. Okay. So, we will deal more with the uniaxial crystal, okay, not so much with the biaxial, because again the derivations and formula and everything becomes a little more complicated with 2, and we can understand most of the processes within this uniaxial crystal. Okay. And this is a special type, I will be dealing more with that, which is an ellipsoid of revolution about the third axis. Okay. So, this is one axis and it is an ellipsoid of revolution like this. Now, see. Now, here I have just separated out into the extraordinary ray and the ordinary ray. Okay. The extraordinary ray looks like this. This is the ellipsoid. The ellipsoid is sitting inside the circle. Okay. That is also possible. So, if I take a cross section of it, I just cut that ellipsoid and this is what I will get. Okay. So, here N0 is this. N0 is the ordinary ray, the refractive index for the ordinary ray. It is same in all direction, all around in the circle. And Ne is the refractive index for the extraordinary ray, which follows the principles or the rules of this ellipse. Okay. Now, since this ellipse is sitting inside the circular piece, it is called a negative crystal. That means NO refractive index is greater than NE refractive index. Okay. This is just a classification of crystals, one more classification. You could have another classification where the ellipsoid is outside and the sphere is inside. The sphere is inside means N0 is less than NE. Okay. N0 is less than NE. Such a crystal is called a positive crystal. Okay. So, generally you have crystals which have 3-fold symmetry, 4-fold symmetry. When we say 3-fold, 4-fold, for a crystallographer it is very important to know which fold symmetry comes into the picture. But for an optics person, one of these symmetry lines is the optic axis. So, the optic axis has a physical character to it. It is not completely imaginary line. It belongs to one of these folds of symmetry, okay, in crystals. Now, So, here I have just distinguished the ordinary ray and the extraordinary ray. So, quartz is a positive uniaxial crystal, which we have seen before. KDP and calcite is a negative uniaxial crystal. Okay. Both are uniaxial. Now, KDP was the most popular one, if we have seen that. It gives second harmonic for quite a few laser wavelengths. Okay. Here I have just put down the O ray follows Slen's law and the E ray does not. Equation of the ellipse cross section in Cartesian coordinates is this. See, it is this ellipse, okay, this ellipse or even this ellipse. I have just taken a cross section of this ellipsoid. Okay. And the equation of an ellipse, you know, x square upon n0 square, y square upon ne square equal to 1. These are the principal axes of the ellipse. Now, in polar coordinates, if I were to write it in polar coordinates, it would be cos square theta upon ne square plus sin square theta upon no square is equal to 1 upon n square Re. So, we are looking for, we will be for any ray that is passing through the crystal, we would like to know the refractive index for that ray. Okay. So, here I have shown it here. This is the direction of the ray in which it is travelling. So, obviously, it splits up into the O ray and the E ray. The O ray will obviously have NO as the refractive index. Everywhere, wherever it goes, it has NO. But then what about the E ray? Suppose it is going in this direction. It will depend on the angle theta, this angle theta. Okay. Now, from where do I measure this angle? I measure it along the optic axis. Here the optic axis is here along this straight line. So, my optic axis is the reference point from where I measure the angle theta. Okay. So, I measure this angle theta here and that is how it is. Okay. So, I know the refractive index for the E ray and for the O ray. Now I come to achieving phase matching condition. The permittivity epsilon increases with frequency in a dielectric material, and so even n omega, the refractive index, increases with the frequency. So, n 2 omega is always greater than n omega. One cannot achieve phase matching in any material. However, in an anisotropic crystal, by means of a trick, the phase matching condition can be realized. Okay. This is a section of a sphere. Okay. It is an isotropic crystal. So, the one inside is for the refractive index for n omega. Now, for n 2 omega, it will be this circle. So, it will increase, the refractive index will increase with the increase in frequency. So, you will keep on getting circles, concentric circles. So, when can I get n 2 omega equal to n omega in order to have delta n is equal to 0? If this is this, suppose I take it even for the anisotropic crystal or for the extraordinary ray. It is following the rules of this ellipse. So, even for the extraordinary ray, I have n refractive index omega is this ellipse, refractive index 2 omega is this ellipse. This is the section of the ellipsoid. So, whether for the ordinary ray or the extraordinary ray, I am not getting n 2 omega is equal to n omega. Okay. So, in an anisotropic crystal, this is what is happening. In an isotropic crystal, this is what is happening. Okay. Now, what should I do? That is where I take the birefringent crystal. So, in the birefringent crystal, you have the ellipse and you have the circle here, the sphere here. Okay. So, if I were to take a cross section, this is what I would get. Okay. There is a circle and there is an ellipse, and there is a point where they cross each other. See, this circle corresponds to NO2 omega. This circle corresponds to ordinary omega. Okay. This one corresponds to NE, this corresponds to NE. I have not written it on the, this is NE, this is for the extraordinary ray. Okay. So, here is where it crosses, see, Ne2 omega Ne2 omega, which is this, crosses with NO omega. Okay. This is the point where it goes. So, if I put a ray of beam in this direction, I will get N2 omega is equal to N omega, and that is the condition I am looking for. That is why I need a birefringent crystal. Phase matching condition is achieved in a birefringent crystal. Delta N is equal to 0, N2 omega is equal to N omega. So, I have to pass my ray into that crystal such that it makes an angle of theta with respect to the optic axis. The optic axis is here. Once I do that, I have got the phase matching condition, and there I get a large intensity of second harmonic generation. Okay. So, phase matching condition is achieved.